So silicone's in the middle of it.
Yes. So when you're working on these electron dot structures on page 15, if you're having a hard time picking out which one goes in the center and which one goes on the periphery or on the outside, think about, look at the valence electrons. How many valence electrons does silicon have? 4. And how many valence electrons does fluorine have? 7. Okay, so think about it this way. The one that has the least number of valence electrons, with the exception of hydrogen, is going to be in the center. So this one's going to be in the center.
And it also doesn't have a number behind it. It's like SI2. I mean,
Right.
So it stands out by itself. There's only one of them.
That's
how I
another.
remember it.
That's a good point. So with this electron dot structure, you're going to have silicon to fluorine. Now be careful. A lot of times students will just put one F and not 4 Fs. That 4 means there are 4 fluorines. So 1, 2, 3, 4. You tally it up when you have 7 times 4, but just be aware, it's easy to forget on your electron dot structure. So you have 7 times 4, that gives you 28, plus 4 gives you 32 electrons. So you should have 32 valence electrons in this electron dot structure. Right now, I only have 2, 4, 6, 8. So I need a lot more. Silicon is the only atom in this electron dot structure that has an octet. So we need to give fluorines the octet. So give out your electrons. So 2, 4, 6, 8. Now that fluorine atom has an octet. Do the same for the rest. So give all your fluorines octets, and then do your electron tally. So make sure that you don't have more than 32 electrons.
Do you care what line or the dots? Doesn't matter.
It doesn't matter. So I could have dots here or lines. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 30, 32 valence electrons. So because I have 32 valence electrons and that's all that I was budgeted out, I don't put any lone pair electrons on my central atom. If I had extra remaining, then I would put them on my central atom. Questions on that one? All right, this next one, CF2Cl2. If you're having trouble getting started and picking out which one goes in the center, look at your valence electrons. Carbon has how many valence electrons? 4. Fluorine has 7. Chlorine has 7. 2. So the one with the lower number of valence electrons is going to go in the center.
Isn't carbon usually in the center too? It's like a carbon chain.
Yes, carbons are usually in the center. They like to share those electrons, and so you could have either the lines or the dots, whichever is easier for you. Carbon forms 4 bonds, so if it makes it easier, you can have your 4. And then it does not matter where you put your chlorine or your fluorine. They can be alternating, they can be the same. So you could have your chlorine here, your other chlorine opposite. Fluorine here, fluorine here. How many valence electrons do I need to have in this electron dot structure? 32. So 32 again. So give your halogens, your fluorine and your chlorine, give them all octets. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 32. Does everybody have an octet in this electron dot structure? Yes, so it looks good. Questions on this one?
Only question is, so conceptually wise, when they're all octets like this, and it's almost kind of like a perfect bond, it can't, like, if something were to come in, it can't. It's not readily easy for it to bond with something else. Like something would have to be a catalyst, to almost like force this to
break
remove
it
something.
apart. Yes.
Okay.
All right, what about NF3? Nitrogen has 5. Your fluorines have 7 times 3. So you have 26. What's going to be your central atom here? Nitrogen. So you know, because you have 3 fluorines, how many bonds are you going to have? 3. Then you'll have your fluorines. Then you're going to give your octets to the peripheral atoms. So 2, 4, 6. At this point, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4. So I have 24 electrons shown. Now I have 2 remaining to give out. Where do they go? On top of the nitrogen. So nitrogen has lone pair electrons. So those are non-bonding electrons. Questions? So remember, covalent compounds are between what and what? Non-metal to non-metal. Say it a million times if you have to. We're going to learn how to name covalent compounds now. So I will either give you the formula of a covalent compound, and you need to write its name, or I'll give you the name of a covalent compound, and you'll need to write its formula. So just like with the ionic nomenclature we had earlier. So the first step in naming covalent compounds is to name the element in the formula using a prefix needed to indicate the number of atoms. So the prefixes are here. 1 is mono, 2 di, 3 is tri, 4 is tetra, 5 is pentat, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. Good. What's that?
I just said
That's good stuff.
yeah, exactly.
So the second step is to name the second element using the IDE ending with prefixes if necessary. Now, I have this sentence above, and you're like, what does that mean? Molecular formulas are written with the less electronegative element first. Remember that molecular formulas, this is non-metal to non-metal. So let me just use this example. So if I have CO2, usually the first element in this molecular formula is less electronegative. What does electronegativity mean? That means how much they attract electrons to themselves. We'll go over that coming up. But carbon is the less electronegative. And where you find the electronegativity, not such a big deal for what we're doing right now with nomenclature, but this is very helpful for predicting the types of covalent bonds. So we will use it in Unit 2. If you look at the funky side of your periodic table, the side that we have not been using at all, this is the side that if you turn to it, what language is this? I don't understand it. There are these numbers. I don't see any atomic numbers. I'm looking for the atomic numbers. The electronegativity is the number in the top right-hand column. So with CO2, you see that carbon has an electronegativity of 2.55. Oxygen, on the other hand, has an electronegativity of 3.44. So oxygen is more electronegative.
So noble gases are negative. Sorry, or no,
Right. Okay. So I went over that just so when I show you again, it's not so shocking. To name CO2, you guys have all heard it said before, I'm sure. It's carbon dioxide. So carbon dioxide. On the next page, I have practice problems. So the first one is carbon dioxide. The second one is carbon monoxide. That's the one you want to stay away from breathing. So, competes with oxygen. You hear all these stories in the news of carbon monoxide poisoning. 3, sulfur dioxide. So in terms of what you're using compared to ionic compound nomenclature, it's not as difficult. It's definitely, oh, okay, I see this. It's when you combine the two that it gets tricky. So you need to practice mixing them up. And I have a lot of practice problems on the following pages. Number 4, what's number 4? Sulfur trioxide. If you only have one atom, the first atom is only one, you don't say monosulfur trioxide. It's just the name. However, if you have more than one atom, as in number 5, N2O, you say dinitrogen monoxide. So then I want you to work on the rest of these on page 17. All right, how did you name number 6? Nitrogen monoxide. Number 7, dinitrogen trioxide. Number 8, nitrogen oxide. Number 9. Good. Dinitrogen tetrox. Now, so this is tetra plus oxide. Instead of writing tetraoxide, you get rid of the first vowel if you have two vowels going together, so tetroxide. And then same thing for number 10, dinitrogen pentoxide. And then number 11, phosphorus trichloride. Number 12, carbon tetrachloride. Sometimes you'll hear this compound referred to. It's a carcinogen, but it was used not that long ago, actually, for organic chemistry. It was used often as a solvent. Carbon tet. Stay away from it. But my advisor in graduate school was like, "Oh, carbon tet's not that bad," and it had like all these warnings: "Do not use." We used to use that all the time. I wouldn't wear gloves. Wouldn't work in a hood. Those were the good old days of organic chemistry. Number 13, phosphorus tribromide. Excellent. So on the following pages, I have practice problems, 18 and 19. These practice problems, I want you to work, for the next class meeting. What is unique about these practice problems is it's ionic and covalent mixed together. And this is the most challenging aspect of nomenclature, because a lot of you seem to, pretty quickly pick up on covalent nomenclature, where you use the prefixes, not so bad. It isn't so bad, but once you have them all mixed together, it gets confusing. And I have a lot of students who, they get in the covalent mindset, and then they name everything covalently. So sometimes I'll get experiment 8 handed in to me, and I can see, dilithium phosphate, for instance, or trilithium phosphate might be how they name it. So just be careful going through this. Ask yourself, what type of bond is it? Is it ionic or is it covalent? And then that tells you how to name it. So I will have the answers for these at our next class meeting. And then we'll move on to page 20. And this, I touched on this a little earlier, electronegativity. So we know in covalent bonds that electrons are shared. But how are they shared? You have that one friend that you talk to, and they're always needing something from you. You're friends, you're sharing a lot, but there's always, you just feel like you're always giving. And it happens that in covalent bonds, there is a type of bond where electrons aren't shared equally. So one atom hogs the electrons instead of sharing nicely. So if we look at hydrogen and chlorine, and look at the funky side of your periodic table. If you look up the electronegativity for hydrogen, and that's very glary right now. So hydrogen has an electronegativity of 2.10.
Ours says 2.
2.20. Okay, let me put 2.20. Then it's not that big of a difference, but I don't want it to confuse anybody. All right, and then chlorine. What do you guys have for chlorine? 3.16. So if you look at this dot structure for hydrogen chloride, another name for this is hydrochloric acid. And I need to fill in my dots here because hydrogen is 1 valence electron, chlorine is 7 valence electrons. So if you imagine that this electron density between hydrogen and chlorine, so these two electrons that are being shared, you imagine it like a rope. And these atoms are in a tug of war. And one is, if the atoms are of equal strength, then you know that you're at a tie. Nobody's winning this tug of war. However, if you have olive oil on one end and Popeye on the other, who's going to win that tug of war? Olive oil. Oh, yeah, you won. Well, it depends. Popeye's eating the spinach, right?
There you go.
Yeah. So
He's pretty clumsy with that.
I know.
There's a Family Guy spoof where they said that those were giant tumors in his arm and his stutter was from a stroke and they just gave him medical problems for everything.
I'd see that one. So if you assume that Popeye has eaten his spinach and he's in this tug of war with olive oil, he would definitely win this tug of war. And that's what happens with atoms. There are some atoms that are better at attracting electron density to themselves. So they hog the electron density. So a polar covalent bond occurs when electron density is unequally distributed. So if you look, chlorine has an electronegativity of 3.16. Hydrogen is 2.20. Chlorine is your Popeye. And this after eating spinach. So chlorine can hog that electron density. So the higher the electronegativity value from your periodic table, the more readily they can pull that electron density to themselves. The atoms can do that. So electronegativity is the ability to attract electron density. So, you know, depending on which atom you're looking at, some will have high electronegativity, some will have low electronegativities. So the higher the number, higher En, the more electron density. So a polar covalent bond is when electrons are shared unequally. So there's not equal sharing of electrons. So unequal sharing of electrons. So I want you to look up the electronegativities on your periodic table for each of the following bonds. All right, so what did you find out for carbon? 2.55. And nitrogen? Okay, so 2.55. And oxygen is 3.44. And then chlorine is 3.16, 3.16.
I think I just got the trend. As you go from left to right, the electronegativity gets larger.
do it from bottom to top. Yes. Oh, thank you for reminding me of that. So when you are asked to classify a covalent bond, there are guidelines. So if you have an electronegativity difference, and this is on your periodic table too. Sometimes it's hard to say whether something is one thing or another. You know, there's a gray area. You can kind of say the same thing when you look at electronegativity. We're looking at the difference in electronegativity. If it's a large difference in electronegativity, then it's more than likely ionic. So, you know, if you look at sodium and chlorine, or chloride, so of sodium chloride, so sodium is 0.93 and chlorine is 3.16. If you calculate the electronegativity difference, the difference between those two values, so 3.16 minus 0.93, you end up with an electronegativity difference, and that's a triangle, if you can believe it, 2.23. We know sodium chloride is an ionic compound, right? Metal to nonmetal. So electronegativity differences of up to 1.9 indicate polar covalent bonds. So if you have an electronegativity difference of, so less than 1.9, but greater, and if these inequalities are confusing for you, just hear me out, and maybe we'll be able to work a different symbol out. Greater than 0.4, this is a polar covalent bond. If you have an electronegativity difference I'm going to say greater than 1.9 right here. Greater than 1.9, it's ionic. You have an electronegativity difference less than 0.4, then it's a non-polar covalent bond. So go through for each of your atoms, carbon, nitrogen, carbon, oxygen, chlorine to chlorine. What can you say for sure about chlorine to chlorine? What type of bond is it? This is non-polar covalent. So you get an electronegativity difference here of 0.89. How would you classify carbon-oxygen? Polar covalent. And then carbon-nitrogen, 0.49. So that would still be polar covalent. So this is the one time where you're going to be looking at the strange side of your periodic table, and that's okay. The trend on your periodic table, as you go from left to right, and you will always have the electronegativities available to you, so you don't have to memorize this trend, but it's interesting to know. So you go from left to right in the periodic table, you see increasing electronegativity. So fluorine is the most electronegative element, or electronegative atom. It's almost at 3.98. And then as you go from the bottom to the top of your periodic table, you'll see electronegativity increase as well. Any questions about electronegativity? Right. Let's go. We're going to go through these last two objectives and then stop. So the mole and the number of moles, we're going to define what a mole is, determine the number of moles in each element in a given formula. We're going to determine the molar mass of a substance and use the molar mass to convert between grams and moles. So it turns out there is a day called Mole Day, and it happens in the fall. Mole Day, and when we get to how I define a mole too, it'll make sense. Mole Day is on October 23rd at 6:02 a.m. So you get this on your computer, or you'll see messages about Mole Day. The reason is because a mole of something is 6.022 times 10 to the 23rd. So it has to do that. It's very dorky, right? Oh, I'm celebrating Mole Day. A mole is used in chemistry. It's kind of like the dozen of chemistry. So, in cooking and baking, you hear the dozen. That's 12. Baker's dozen, 13. The mole, we'll go through some exercises to give you an idea of what the mole is, but it's very useful. So let's say I have a Chem 122 class that has 200 students. One day I decide to bring in jelly beans. I want each student to have 10 jelly beans. How many total jelly beans would I need to bring in? 2,000. So a lot of you can, do this right away. You know it would be 2,000. So let's set it up, 200 as a conversion. Good practice from Unit 1. 200 students over 1. And I want each student to have 10 jelly beans. So 10 jelly beans per student. So that would be 200 times 10 would give you 2,000 jelly beans. So it would take me a long time to count out all those jelly beans. And I'm sure my students want to appreciate me touching them, right? However, if I knew how many jelly beans were in a pound, that would be a lot easier. That way I wouldn't have to count them out. So it turns out there are 400 jelly beans in 1 pound. How many pounds do I need to weigh out in order to give my class the 10 or each student 10 jelly beans? So if I want 2,000 jelly beans, and I have this conversion factor, 400 jelly beans in 1 pound. And I think this is the Jelly Belly brand of jelly beans. I don't know if other brands would have the same number of jelly beans in a pound. By the way, Jelly beans, I one time went to my husband and I visited the factory where they make Jelly Bellies. Has anybody ever done that? unbelievable how much sugar they use.
It's almost all sugar.
Oh, yeah, it's all sugar, but then it cracked us up because it was like a coat of polishing sugar to get that shine, you know, and then like another coat of sugar. Just rotating and rotating with sugar, but
It's insane the flavors they have.
I know, yeah.
Who was that at?
I think California, somewhere.
There's a Jelly
It's San
Belly
Francisco.
store. I don't know if it's a factory too, but there's like a Jelly Belly emporium in Wisconsin somewhere. My cousins go all the time.
Yeah.
They love brownies.
All right. Okay, back. What were we doing? Oh, 400 jelly beans in 1 pound. And okay, so 400 jelly beans, and then 1 pound. So it would be 5 pounds of jelly beans. So if I weighed out 5 pounds, then I know that I have enough for each student to have 10 jelly beans. So we use the same reasoning in chemistry. It is very difficult to count atoms. Remember, atoms are very small and very tiny, and it would be really annoying to have to count them all out. So, so we frequently weigh elements knowing exactly how many atoms we should obtain. So if you look at your periodic table, not the funky side of your periodic table, the periodic table that you're more accustomed to using, if you look at the atomic weight for phosphorus, this is the red number that I told you not to look at last unit. It's 30.97376. Or is that what yours is too? Where I got this periodic table. Okay.
973,762.
So 30.973,762. Let me just 973,762. All right. It turns out that 30.973,762 grams of phosphorus is 1 mole of phosphorus atoms. So when you pull this atomic weight off your periodic table, put units on it of grams per mole. That makes sense? So grams per mole. And you don't have to carry all these decimal places because it would be very confusing. I am happy when you're looking at atomic weight or molar mass if you just say 30.97 grams per mole. So instead of having to count out all these atoms, you could just weigh them and you know that's 1 mole. Remember I said 1 mole is like a dozen of chemistry, or a dozen in chemistry. So 1 mole, and this number is referred to as Avogadro's number, is defined as 6.022 times 10 to the 23rd units. It depends on what those units are. If you're dealing with an ionic compound, it's ions. If you're dealing with a covalent compound, it's molecules. So that's why it's not ions or molecules. It depends on the compound. So if I weigh out 30.97 grams of phosphorus, that means I have 6.022 times 10 to the 23rd atoms of phosphorus. So that is a lot of atoms, but you could not count them because they're so small. So I have this question for you at the bottom of page 21. If I want to make 1 mole of sodium chloride, how many moles of sodium and chloride do I need? What's the formula for sodium chloride? PbCl. Right. So these subscripts are the molar ratios. So I would need 1 mole of sodium, 1 mole of chloride. Now, if I was asking you about a different compound, let's say PbCl2, in order to make that compound, I would need 1 mole of Pb. How many moles of chloride? 2 moles of chloride. So these are molar ratios when you're dealing with compounds. Whether it's a molecular formula or an ionic compound, ionic formula, those are molar ratios. So the next page, I have molar mass. What is molar mass? This is the number of grams in 1 mole of something. Whether it's a compound, whether it's just a pure element. The units on molar mass are always grams per mole. You get the molar mass off your periodic table. So you obtain from your periodic table, and then I have, yes, it's okay, because in Unit 1 I was so adamant about not using the molar mass.
So now what you called atomic weight is now molar mass.
Mm-hmm.
You said you wanted to round to the hundreds place.
Round to the hundredths. Round to the hundredths place. And the exception is hydrogen. Take hydrogen to the thousandths. Hydrogen should be 1.008 grams per mole. Everything else you can just round to the hundredths. I'm going to go a few more pages and then I'll give you a break. So it won't take that long. The molar mass, I want you to calculate the molar mass of these 3 compounds. I will go through the middle one with you so you get an idea of what you need to do. So when you have a molecular formula and you're trying to calculate the molar mass, or an ionic formula as well, you're going to be paying close attention to the subscripts. So I always kind of make a tally like this. So I have 12 carbon atoms, and then the molar mass for carbon is 12.01. Then I'm going to do the same with hydrogen. I have 22 hydrogens times 1.008. And then oxygen, I have 11 oxygen atoms times 16. So when you enter this in your calculator, you can enter it in steps, or you can enter it in one whole entry. If you do one whole entry, be sure you use your parentheses appropriately. So 12 times 12.01 plus 22 times 1.008 plus 11 times 16 . And then round your answer to the hundredths. So 342.296 would give you 343.30 grams per mole.
Maybe 3.2.
Oh, yes. Oh, crazy rounding I did. Thank you. 342.30. Is that clear how I went about calculating the molar mass? Good. I want you to calculate the molar mass of potassium fluoride and then ammonium dichromate as well. So potassium fluoride, what did you get as your molar mass for potassium fluoride? 58.10, so you have potassium at 39.10 plus fluoride, call it 19. 58.10, and the units on that are grams per mole. Now, ammonium dichromate. What? You got to get the formula out first, right? Yeah, I'm stretching you guys. You've been listening to me for a long time. Really? Okay, ammonium is NH4, positive 1. Dichromate is Cr2O7 minus 2. Do the cross and drop. You come up with your formula, NH4 parentheses 2, Cr2O7. Now, in terms of calculating the molar mass, you got nitrogen, hydrogen, chromium, oxygen. How many nitrogen atoms do you have? 2. That 2 outside the parentheses multiplies the inside. So 2 times 1 gives you 2. So 2 times, and then nitrogen is 14.01. How many hydrogens do we have? 2 times 4. So you have 8 times 1.008. Chromium. How many chromiums do we have? 2. And that is, good, 2 times 52.00. And then oxygen. How many oxygens do we have? 7 times 16. So if you didn't come up with the right formula for this one, you might have the incorrect molar mass. It would be what?
Be racing to get this stuff done in 15 minutes of my exam.
We won't ask you a ton of questions. It would just be like one or, here and there. But so 252.08 grams per mole. Questions on those? I'm going to do this last page. And rest.
Is that like the more, is that like the most like difficulty that we're kind of responsible for, or do you know like the book problems that follow the chapter go farther than that?
You'll see examples like this,
Like that?
but just know that when you have a coefficient outside the parentheses, you need to multiply it by the subscripts. Yeah. All right. What are the units on molar mass? Grams per mole. Think of molar mass as a conversion factor. The number in molar mass is married to grams. So I say that, it might not make sense. 252.08 grams per mole. That 252.08 is married to that grams. They're not getting a divorce. I say that because sometimes what happens when students get into molar mass, they'll flip this around. Put 252.08 with moles and 1 with grams. That's not how it works. So when I say it's married, they stay together. That's what I mean. If you need to flip this conversion factor, flip the units as well. Grams, 1 mole. So this kind of goes back to our Unit 1, where we're doing conversions. Now remember, chemistry is a science of conversion, so you see it over and over again. So if you had a starting quantity in grams, how would you convert it to moles using molar mass? So if I have so many grams over 1, molar mass, remember, can be grams over moles like this, or moles over grams like that. I would need to flip my molar mass in order to get the grams to cancel out. So I flip molar mass. Now if I had a starting quantity in moles over 1, I don't need to flip the molar mass. Just get it to cancel out that way. So on the next page, I have problems that you are determine the number of moles in each of the quantities below. So you need to convert the grams to moles. So I'll do numbers 1 with you. 25 grams NaCl. It's a good idea not only to write the unit, but what the substance is that you're dealing with. In order to get moles from this, what do I need to look up for sodium chloride? The molar mass. So the molar mass for sodium chloride, you have sodium at 22.99 and chlorine at 35.45. So I get you 58.44 grams per mole. Sorry about that. Do I multiply or divide by that? Divide. 58.44 grams, 1 mole. So sig figs always come into play. Base it off your starting quantity. Your answer cannot have more than 2 sig figs. So 0.427. So it's going to be moles of NaCl. Good. Now, I'm going to go through number 1, the second part with you. Determine the number of grams. So my starting quantity in the second part is going to be 2.5 moles. I'll use the same molar mass, 58.44. Will I multiply or divide by the molar mass? Multiply. So 2.5 times 58.44. 146.1 grams. How many sig figs do I use? 2. Excellent. So 2 sig figs, 150 grams, and I didn't put my NaCl. I want you to work on the rest of these for Wednesday.